Welcome to the machine learning compilation class, everyone. So today we are going to begin the first journey of this lecture series. My name is Tianqi Chen. You can call me TQ. I will be with you together on exploring this new emerging topic. So today's lecture is going to come into two components. First, we're going to talk about what is machine learning compilation techniques, why we want to study them. Then in the second part, we're going to dive a bit deeper onto some of the key elements that we will be using in the next few part of lectures. So to begin with, why study machine learning compilation? If you look at the software landscape nowadays, you can find that the software that we are living in the age of artificial intelligence is very different from a software that we used a few years ago in the age of Web 2.0. So previously, we are looking at softwares that have wide a range of application scenarios. Most of them are built on a smaller set of software libraries, and finally they are running on some of the core foundational piece on a single piece of device. Usually that's a general purpose computing device like on your laptop or on your desktop. And in this case, the software requires to have broad coverage, where engineers handle most of the performance optimizations and other cases, and the compute is less critical and it's mainly about how do we get as wide a variety of applications as possible for your laptop and for your web experiences. However, if we start to look at the software landscape at the age of artificial intelligence, a lot of things have changed. Specifically, the software landscape starts from what is like a funnel type onto a more wider range of both the front-end applications that are specialized, as well as the backends that we want to run it on. First of all, in the age of AI, what we are trying to build and run are machine learning models, such as object detection models, natural language processing models in different forms. Usually those models will need to ingest a bigger amount of data set so that we will be able to fuel them with AIs using learning from those data sets. And one of the key requirements there is that we want to be able to handle those models on a wide range of hardware devices and environments. Those devices could include simple settings such as the normal data center CPUs, as well as some other more specific settings like this specialized TPU port, or in certain cases, this computing start to sit in your pocket, like the iPhones or other devices that we'll be using. And this shift of computing paradigm really requires us to rethink how do we build software in the age of AI. And that's where the topic of machine learning systems, in particular in this lecture, the machine learning compilation, jumps in to become a quite relevant topic that we're studying in today's age. Okay, so what is machine learning compilation specifically? If we want to talk about machine learning compilation, we want to start to think about what does it involve to take what we say intelligence application and try to put them onto those environments we call deployment environment we are interested in. So there are, as we know, in a lot of cases, machine learning have been used in a lot of cases, and with the recent success of deep learning, there are quite a lot of smart applications that become part of our daily life. For example, the emergence of driving car case will require us to do things like object detection and pedestrian detection, segmentation. If we say hi Alexa, or using other smart devices like Siri, it involves machine learning model that does natural language processing and speech recognition. More recently, there's also exciting news that uses AI to be able to fold proteins so that we'll be able to get more information that help us towards new scientific discoveries, as well as finding effective medicine drugs for some of the new emerging diseases. One of the key characteristics now is that now those machine learning models are running on really wide range of environments that are interesting. For example, in the case of self-driving cars, usually we want to be able to run those machine learning models, the detection models, and some of the planning modules on the cars themselves. Usually that will involve specialized computing devices on the car. In the case of protein foldings, maybe we want to be able to run them on data centers so that we'll be able to fold them. We'll be able to find some of the sequences. But in other cases, maybe we want to run those machine learning models on DNA sequencers or other specialized devices. If we look at NLP and speech recognition, some of them have to run on those smart devices, such as smartphones and some of the smart speakers in there. So there's quite a big of gap that we're looking at actually between those intelligent applications and the deployment environment on the right hand side. Now, if you start to think about it, I want us to pause a second and think about what are the possible complications that involved in to bring some of the intelligence applications on the left hand side to the deployment environments on the right hand side. There are a lot of heavy liftings going on, and a lot of these are non-trivial. If we start to think about some specific factors, you will find that some of factors will include things like the hardware choices that might be relevant in this case, what kind of operation systems that involves, in running those things, the container execution environment, and sometimes the runtime library variants, and whether or not accelerators are involved. All those factors need to be factoring together to be able to make that effort of taking machine learning models that we build in development settings onto the deployment environments that we're interested in. Previously, this process is really, usually done in a more manual labor process. So for each kind of application scenarios, there will be a dedicated team of engineers that takes in these machine learning intelligent applications and trying to bring them onto a deployment environment. And that is still the case today. However, one of the questions we really want to ask as this practice becomes more and more common is that, is there any way for us to simplify such kind of machine learning deployment problem and really help us to be able to innovate more, bringing in a lot of the latest, greatest machine learning models, but also bring them onto many of the latest, greatest environments that that we want to put AI onto. And that's kind of the main thing of today's lecture, which is called machine learning compilation. So specifically, machine learning compilation refers to the process where we want to develop our models. So there will be, machine learning models in its development form. Usually, if we look at some of the machine learning model developments, there will be one engineer or a few engineers working together on building models, usually on common machine learning frameworks, such as PyTorch, TensorFlow, or JAX, or other favorite frameworks like XGBoost and so on. And the question is, how can we take that machine learning model in its development form and try to transform that onto what we call a deployment form? In this particular case, the deployment form refers to everything that we need to be able to deploy that particular machine learning execution. For example, on this right hand side, here's a specific example of how we can take one model from its development form and try to put that on an Android device. And this is just an illustrative example, but it shows some of the complexities in behind the scene. For example, first of all, in order to put that on the Android device, we kind of need to try to build the intelligent application and expose that to the interface that Android accepts. Usually that's a Java developed environment. When we are trying to pack these machine learning models, it usually comes with description for some of the execution engines that involves how we are going to compute each steps of the machine learning model. Of course, in order to compute that, we also need to store the weights that are learned through the development process in order to really make that effective execution. Besides those, we also need to be able to have relevant libraries that allows us to run that execution. For example, in this case, we are only giving a few examples of what are possible libraries in here that trying to implement some of the operations, such as matrix multiplication, softmax, and other operations that common machine learning models uses. And finally, those libraries will need to be run on some of the environments that execute those. For example, if you want to leverage the on-device GPU that comes with the Android devices, then we want to be able to run them on things like Android OpenCL runtime, or maybe if there's a native acceleration going on through some of accelerators, we might need to leverage some of the native libraries such as Android NA API. Of course, some of those concepts may not be, you may not be familiar with all those concepts. That is totally fine. This is just an example of illustrating some of the key components that could be involved in deployment form. And you can find the key components include both some of the system components that are specific to the platform, like API interface and operation system interfaces and so on, as well as machine learning model specific information such as descriptions and weights. And if you're not familiar with a specific term, you just need to understand that we need to be able to find deployment form in both the runtime system specific factors as well as the machine learning model specific factors. Okay, so the machine learning compilation or MLC process is a process. We have not yet defined how we do it, but it's a process that helps us to transform the machine learning models from its development form on the left hand side to the deployment form on the right hand side. And importantly, this MLC process doesn't necessarily have to be fully automatic. For example, we could say, if I'm a developer, I'm going to identify these higher level machine learning models like object detection model. I'm going to hand wave everything and package them together and put them in deployment form. We still call that process as machine learning compilation, except that this compilation is done with engineering involvement. As a matter of fact, a lot of the current practices in deploying machine learning models involve that kind of manual process anyway. On the other hand, we are also interested in other automated solutions that help us to automate some of the solution and generalizes some of the methods that help us to transform and optimize machine learning execution. Okay, so here's the high level on what MLC means. It means that we want to be able to take models from development form and trying to do transformations and get them onto the deployment form. So next, we're going to talk about what are the key goals that we need to achieve throughout this process. What can MLC brings you through this process of transforming from development form to deployment form. So the first goal of MLC is that we want to be able to help us to interrogate together a lot of the solutions for that deployment form and also minimize the dependencies. So in this particular case, we are on the left-hand side, let's assume that we are trying to build a machine learning model for computer vision. We have not shown exactly what the model is, but let's just use this rough figure to show, here's a model that contains, 1, 2, 3, 4 layers and 1 input. And it is built using some of the modern machine learning frameworks like, PyTorch or TensorFlow or JAX. Usually those modern machine learning frameworks contains a lot of features that allows us to be able to support all kind of machine learning model operations, such as, in the case of computer vision, usually involves, convolution that allows us to take local pixels and try to group them and find patterns in each of the in a more translational invariant manner. There will also be softmax and activation functions and other operators. So there are features that are necessary to support the models. In the meantime, there are also these frameworks also contains features to support other models. For example, the embedding lookup is usually useful for natural language processing, but not necessary for vision. FFT is usually used for speech recognition, and so on. So one of the goals of machine learning compilation is trying to come up with a deployment form such that we can have a minimal set of artifacts that allows us to support deployment. Specifically, one of the things that MLC might do is we can analyze this machine learning execution, and we find that, hey, only this component is really necessary. So let's also try to come up with a corresponding component on the right-hand side that is minimal to support the model execution. So this is kind of related to the goal of dependency minimization in here. Besides dependency minimization, there's also this perspective intergregation. So this is because in a lot of cases, for example, if you want to deploy models onto devices like mobile and other cases, we might need to leverage libraries and solutions from different parties. For example, this two-dimensional convolution could be implemented by one team of engineers, while the softmax and the ReLU could be implemented by another engineering team. Or usually the key operators of convolution are implemented by vendors who kind of know deeper onto how exactly to optimize those critical ones. We kind of need a way to be able to assemble them together and making them work together in the final deployment phase. Usually this is done by, say, a common execution engine or interpreter that allows us to plug in those additional machine learning operators. So for the first part of the goal, machine learning compilation really aims to be able to interrogate all those backend solutions together and also minimize the possible dependencies. So we can really come up with a deployment artifact that is minimal, but also sufficient to build our model execution. Okay, so that's the first goal. The second goal of machine learning compilation is to leverage hardware native accelerations. So in a lot of cases, when we're trying to bring in machine learning models and trying to put them onto deployment form, we are looking at cases where those deployment environment contains hardware acceleration, such as NVIDIA's Tensor Core and Google's TPU and other cases. And in those cases, we need to be able to generate deployables that really leverages those native hardware backends when possible. By doing that, we will be able to get a solution that is end-to-end, but also takes the best use of underlying hardware. So that's usually the second goal of machine learning compilation. Of course, in general, our third goal that summarizes everything else is that we are interested in optimization in general. In terms of one machine learning model, you may have noticed that there are many ways that we can use to run the same model executions, but each way may come with different execution efficiencies. And one of the goals of machine learning compilation is to be able to take the model from development form and trying to do second transformations such that it help us to do optimization in different cases. For example, one of the goals could be we want to go and minimize memory usage. In other cases, we are interested in improving execution efficiency. Or in other cases, nowadays, if you want to really build bigger models, we're interested in scaling to multiple heterogeneous devices. So this could be all the goals that a machine learning compilation cares about. Okay. And coming back, one of the things I do want to mention is that there's not a strict boundary between those goals. For example, we can view this dependency minimization as well as hardware native acceleration as a form of optimization. It's just like these are kind of quite interesting cases that we want to lift them out and talk about separately. The term compilation in MLC comes from analogy to traditional compilation, in the sense that if you think about traditional compiler like GCC or CLAM, effectively they are taking the code or program in this development form being developed by software developers and compile them onto executables or libraries or other forms that we can use to deploy onto our real-world settings. However, although we call it compilation, the techniques involved behind the scene can be very different between these two problems. And that is why I want to take this specialized course episode to talk about some of the insights for doing machine learning compilation and trying to use those techniques to help us to be able to build better intelligent applications. One of the key things that we do want to notice that also we call it compilation, this process doesn't have to necessarily involve code generation. For example, in a lot of cases, the deployment form can simply be a model description and an engine that executes it natively. And this is actually the most common case that we are using to deploy machine learning applications nowadays. However, in a lot of cases, code generation comes to be quite handy, and we will be talking about some of the code generation techniques as well in our later part of lectures. The second thing is that in some cases, a development form and deployment form can take the same interface. For example, if we are trying to deploy on server settings, maybe we are developing in TensorFlow and you directly deployed in TensorFlow, that is totally fine. Still in that settings, actually, we will be able to leverage machine learning compilation techniques because we will be able to take in the model descriptions in its development form and try to optimize it so that although they expose the same interface, the underlying execution is more memory efficient or being optimized for other metrics we are interested in. Finally, when we talk deployment, one thing I do want to remember is that in a lot of cases we are interested in this scenario called inference, which means that we build a model that comes with model architectures and the model weights, and we're only interested in taking new inputs and trying to make prediction using the model. However, the deployment form can also apply to other settings, like training the model itself. And it has become more and more increasingly popular nowadays when we start to try to generalize some of our artificial intelligence applications. For example, if we want to be able to build a smartwatch that monitors my health, I would like to make learning local on the device and not letting the data leaking to my providers because I care about privacy reasons. As a result, likely we are going to build on-device intelligence executions. And that process can also benefit a lot from machine learning compilation as well, because the process of developing that training process and deployment of that training process can happen at very different platforms. Okay, so here's a generic high-level reason, high-level descriptions about machine learning compilation and the goals that we want to achieve through this compilation process. Let's come back and talk about why do we want to build this course, or why do we want to study this course? There are a few reasons why we want to study MLC. To begin with, one of the things that is really important nowadays, we want to be not only building those awesome models, but we also want to deploy them effectively. And there are a lot of complexity involved in bringing machine learning to production or incorporating novel model customizations so that you can extend your machine learning framework to support the novel model customization that you want. Machine learning compilation really gives us a set of tools that solve those problems. And in a lot of cases, they really come in handy. So that's reason number one to study MLC. Okay. The reason number two is that in a lot of cases, we are developing models and we can just leverage the underlying machine learning framework. However, in a lot of cases, you'll find that those machine learning frameworks are also increasingly start to adopt new techniques coming from MLC. So understanding machine learning compilation helps us to understand the behind-the-scenes techniques that we use to provide those model executions and give us some kind of superpower that really help us to understand how framework works, and sometimes enable us to push novel model customizations with good system support, so that not only we build a smart model, but the model scales with the underlying system. And that is something that many of the machine learning scientists would benefit from in a lot of cases. Finally, if we are a hardware company or we are at the golden age of building hardware accelerations, with waves of new environment innovations coming up. However, one of the key problems of all those novel machine learning acceleration is the software problem. In a lot of cases, we will need to build software stacks from ground up to keep new hardware acceleration features to make best use of them, and also build a spectrum of support for novel models that are emerging. Really, MLC is a way for us to, is a systematic approach for us to be able to build software stack and keep up with all those hardware acceleration and model development innovation. Okay, so that's reason number 3. We have talked about 3 reasons. And one of the last reasons is actually, my reason of bringing this course and working with everybody here is that machine learning compilation is really fun. When I started to study computer science, one of the really revealing moments is that at my, I think, 3rd grade in universities, I started to understand what it does take to take a high-level applications, go all the way through to the compilation process, to the low-level assembly, and how does that run on a silicon. And that is really a satisfying experience overall. When we talk about machine learning, I think it's also interesting to ask, hey, here's a set of AI models. How does that translate to the high-level representations, the low-level code, and to the bare metal mechanism that really runs and supports those intelligent applications? Be able to get that understanding is really what is really self-fulfilling in some sense. And also we can use this tool to solve a lot of our incoming problems. Okay, so here are the 4 reasons that we can study machine learning compilation and also bring some use to our daily lives. Okay, so far we've talked about key elements in machine learning compilation. Now, moving in the next 10 minutes or so, I'm going to spend some time talk about some of the key elements that are involved in machine learning compilation. So in the first part, we have already talked about machine learning compilation is a process for us to take high-level model developments and trying to transform them onto the deployment form that can be executed effectively on an environment of interest. And in order to do that, let's try to dive down another level, and let's start to talk about how does those development form and deployment form look like in practice. Specifically, if we look at most of the machine learning models, there are 2 key concepts that I would say thread through all these machine learning model executions. And hopefully, if you have learned machine learning frameworks, you have already been familiar with some of those concepts. So the first concept is what we call a tensor, which is effectively a multi-dimensional array that stores this input, output, and intermediate results of model execution. So for example, in this particular case on the left-hand side, what it represents is a sequence of computations where we have input tensor that contains 1 by 3072 elements. So it will be something like, if you try to write it out, you have some elements here that have v0, v1, and so on. And there are about 3032 of those elements in that input. And in this case, it's a multi-layer perception network, and we are trying to take in a flattened image on the left-hand side. So originally, it is, I think it's 32. No, it's not 32 by 32. Yeah, 32 by 32 by 3 in images, where 3 is an RGB channel, and we're going to flatten that. That become a vector of 3032 in this case. not only we use this tensor to store the to store the input, we are also using it to store the intermediate data. For example, in this case, we could have a linear layer that tries to project this to a tensor of 1 by 10. So there will be 10 values here, v0, v1, and to v10 in this case, and it represents an intermediate result of that particular layer. Okay, and in here, these tensors are kind of like represents the data that we use throughout the machine learning compilation, through the machine learning execution. Sorry. And now, the second thing that that is really important as a part of the machine learning execution is what we call tensor functions. In this case, the tensor function are operations that encode the computation among those input and output. For example, in here, in this particular case, this linear is a tensor function that help us to be able to take in input and trying to do a linear projection. So the result will be something like output will equal ij will equal sum over k, and we have w, which is a weight, jk times, imagine my input is x, ik. So this is a linear projection layer that help us to be able to take in an input x here and a weight here, and trying to be able to do a linear projection. So if you try to draw that out as a neural network form, it's corresponding to a neural network that includes some of the input vectors as x, and we will have the output as output vector, and we have weights that are fully connected to each of the input. Okay, so these particular operations help us to transform input x with w onto the output in here. And we call it tensor functions. So effectively, it's a set of computations that allows us to ingest in some tensors and output some other tensors. One of the key things I do want to notice here is that this tensor function is not only used to denote a single box in here. So in this case, a single box could correspond to a linear operator, but we can also use it to denote a sequence of operations. For example, in this case, if we try to view what we call a subset of computations. So in this case, if you want to look at this subset of computations in here that contains two tensor operations, we can compose them together, and that's still a tensor function that allows us to be able to run the first operation, that's linear projection, and apply a nonlinear activation, in this case rectify a linear unit to that. And the end-to-end execution of the model can also be viewed as a tensor function in this case. Okay, so when we look at machine learning execution, you can find that most of the things are about tensors and operations that transform among tensors, and that's also the common abstraction most of the machine learning frameworks use to be able to express some of the machine learning computations. So now let's take a look at one example compilation process in the specific terminologies of tensors and tensor functions. So in this case, on the left-hand side, we have the machine learning models in its development form, where we have talked about this is a multi-layer perception that takes in the input flattened image, trying to apply one layer of linear transformation and nonlinearity and another layer of linear transformations. And on the right-hand side, we have one instance of a development form that correspond to the outcome of a possible machine learning compilation process. So I want us to pay specific attention to two places. First of all, if we look at the development form and deployment form, you'll find that on the right-hand side, we have this linear value operations that correspond to actually these two operations working together. So effectively, we are trying to, on this graphic representations, we are trying to put those two things and trying to put them onto a single box that correspond to the right-hand side. And second thing is that on this deployment form, actually, we specifically list out a specialized implementation. In this case, we are using Python to write it out. But in reality, usually it is something that implemented by a lower level code like CUDA or C++ and so on. Okay. So one of the things you can find in this specific MLC process and its outcome is that we'll find that in this process we are trying to transforming this entire thing on the left-hand side, which correspond to a tensor function that we talk about, in that concept, and we're trying to transforming it to another big box in here, which can be viewed as another tensor function, right? So, and one of the interesting thing is that, although they are different in certain sense, they're also trying to do the same thing. In this particular example, hopefully you can say that they correspond to the same kind of computations. So why do we want to do this kind of transformation? In reality, when we're trying to transforming things from left-hand side and right-hand side, it can result in different kind of outcomes in terms of execution efficiencies, memory costs, and so on. For example, in this case, if you are trying to run this code on GPU, fusing those two operations together into a single operation in here will result in less memory copies that goes back to the GPU memory, and as a result, it results in a faster GPU execution. If I've used framework and PyTorch and other things before, you might have seen things like some kind of fuse operators behind the scene is not necessarily directly exposed to you, but when we use things like CUDN and other libraries, they usually come with those fuse operators that we can take benefit of. Okay. One of the things that is really interesting here is that there are really different ways to express the same tensor function. So usually this is a quite common concept in a systems language we call abstractions. So abstraction refers to different ways we use to represent the same system interface, or the same system implementation in certain sense. In this case, we are interested in tensor function that takes in certain tensor objects and help us to output other tensor objects. And there are really different ways to represent it. For example, we could represent it as two consecutive computations where each of the box represent the operations. In certain cases, we can represent it as a single linear value unit, as we have shown in the last part. Or in other cases, maybe we want to represent them as like a sequence of for loops, so that we know exactly how you carry out the computation. In this particular case, you can find that we have three abstract ways to be able to represent the same tensor computation function. And importantly, each of them present a different level of details. For example, certainly this higher level graphical view is certainly more higher level, as you might see, than a loop level, because I could implement the same linear value using different ways. For example, if I swap these two loops into something like for j and then for I, it's going to give me the same program, same program output for any of the input pairs. So there are different abstractions. Some of them are more detailed than others, or some of them are more specialized. In the machine learning system land, we usually say that those more specialized version is an implementation of the abstraction. Now, this concept of abstraction and implementation is going to be the key concept we're going to use through the course of this lecture series. And in a lot of cases, machine learning compilation is effectively a way of transforming among different tensor functions in different abstractions. So specifically, if we think about machine learning compilation, a lot of the things we're going to talk about in the next few part of the lecture episode is going to be about how we can take in tensor functions that that computes those among those tensors and trying to transform them onto the deployment form that are also tensor function but may sit in different abstractions. For example, in this case, at least two kind of ways to represent the tensor function. We have this graphical representation, which we will talk about, which is usually called computational graph. We have this loopy level representation that represents, well, in this case, Python-like program that represents how do we want to compute out the linear ReLU operations. And at least in here, there are two abstractions, right? Or in the terminology of compiler, it's also called intermediate representations that we can use to represent the computation. And usually, a machine learning process, compilation process can be viewed as a transformation among the tensor functions. So we start with a tensor function in the development form, and then we can gradually transform them onto another tensor function that represents more detailed information, such as how I might want to compute the for loop, so on. And usually that can also come in different form of abstractions. In this case, the form of abstraction could be a Python code, a more detailed C code. In other cases, it could be a library function handle, or the underlying assembly code that we are going to go and execute on the hard. Okay, so this high-level idea of abstraction and implementation is going to be something we'll keep revisiting throughout the course of this lecture episode. Okay, and specifically in our class, we are going to visit 4 kind of abstractions. You don't have to, we wouldn't talk about details about each of them, but I just want to give you a high-level guidelines, a high-level view of what we might be able to talk about. So these 4 categories includes the computational graph, tensor programs that correspond to loopy operations, library runtimes that usually are how our vendors try to go and optimize typical machine learning operations. And at the lowest level, there are also hardware primitives that we bake into the native hardware and use those primitives to offer programmable machine learning acceleration. So these are the 4 things that we're going to visit in a later part of the lecture series. Okay, so that's the end of today's overview. In the end, I'm going to end with some of the logistics and disclaimers. So first of all, well, we're in luck, and it's really a fun beginning. It's the first course of its kind, likely in the world. The materials and content as a result are still being developed. So as a result, sometimes we might encounter issues in content assignments. Do bear with us. On the other hand, given this is something that's really exciting about developing it together, it's also a fun topic that we're also exploring together as a community. So I'm really looking forward to chat more about some of those ideas and also explore them together with everyone who in the community to develop this fun topic. In terms of logistics, this is the first episode, and we'll be posting recordings onto YouTube, and all the links will be posted on the course webpage. For some of the lectures, we are also going to have code exercise that help us to be able to understand those detailed abstraction and concepts. Most of the code exercises will be posted on GitHub, and you will be able to find them on the lecture website as well. And there will also be self-contained test cases that you can fork and try and self-assess on how you are doing. And after every lecture, there will also be lecture notes that will be posted to mlc-ai that correspond to written down explanations of some of the things we talk about in the corresponding lecture. Finally, if you go to mlc.ai, there are also links to the Discuss forums. We are going to use GitHub Discuss in this case, and you will be able to feel free to bring in any questions or any thoughts, feedback to the course, and so on. Okay, so this is the end of today's episode. To summarize, machine learning compilation is a process that helps us to take in the machine learning executions in its development form, and we're trying to bring it onto an efficient and compact deployment form. There are several goals such as interrogation, dependency, minimization, leverage our native accelerations, and optimization in general. We have talked about reasons why we want to study ML compilation, including things like giving in-depth view of ML deployment, help us to optimize deployment optimizations, build up software stack from ground up, and importantly, have fun through the process. We also talk about key elements of machine learning compilations. Specifically, most of machine learning execution come with tensors and tensor functions. Of course, in other cases, there will be other objects other than tensors that goes beyond multi-dimensional tensors, but tensors will be the main object of interest. They will come back and visit. If time permits, we might also talk about other additional data structure that can also be interesting, such as strings and other form of tensor data structure. But most of them are going to center around the tensor and tensor function abstraction. And importantly, we have talked about this idea of abstraction and implementations. And in a lot of cases, we can represent the same tensor function in different form of abstractions. Some are more specialized than another one. And the MLC process really trying to figure out how we can take the tensor function in one abstraction, convert it and transform and optimize it to another, which could sit in the same abstraction or different abstractions. And throughout this process, being able to get into implementation that, or a more detailed abstraction that can run on the deployment platform, and finally give us a deployment form that is more effective with dependency minimized and leverage the hardware native accelerations. Okay, so that is today's lecture, and thanks everybody for listening, and I will hopefully we'll see you in the forum, and let's begin this journey together.